Hello, my name is Brian. This is Mina. Can be both presenting about trapping virtual memory today. We both did this research and studied this together. It's actually a really extensive topic, but what is trapping virtual memory? It's a time of check, time of use vulnerability, which is a type of security flaw that happens when a program checks for a condition such as the size of a buffer at one point, but uses that result later on at another point, and can use that gap for memory corruption, privilege escalation, among other things too. This type of vulnerability does rely on time in race conditions, which means it is probabilistic, the results, and success depends relies on between the first check and the second reading, the value changes, and we can exploit that. So it does rely on that. So to maximize that, there's certain ways to do it, but let's look at some code to make sense. So here in this code, we are actually check on line 4 by use the value of the buffer in line 7. Memory corruption can actually happen over here if the result by the input pointer line 1 changes between the first read on line 4 and using that size on line 7 for instances. If the value is read to 100% on the first check, but changes to 400, which is above the threshold to 56 into the buffer, that can actually pass along and be written to the stack, and that can corrupt the stack, leading to exploiting a buffer overflow in that case. Learning a little bit more virtual memory, how that is related to this. How does Linux handle page files by kernel? Well, it depends on the context, but usually when a process tries to access a memory that is not yet present in physical memory, a page file happens, and that is handled by the kernel by either locating physical memory or fetching data from the disk. And whenever the computer is fetching data from the disk, is that something that happens slowly or fast? Usually it's very slow. It's very slow that it can take quite a long time. It might require the defaulting thread to be suspendable. It waits for the page to be read. So we can actually abuse a time window quite a bit. So it can actually be used for a time of check, time of use vulnerability. One of the techniques for using this gap is using a user file descriptor in Linux, where basically this is something that basically it allows applications to receive notifications when a page file happens in the system. And by enabling this, a secondary thread in the process can handle page file in user mode, suspending the file thread until the file is resolved, which means you can actually trap the memory indefinitely in that case. The only downside of using this technique is that it does not work if the code accessing the memory is in a different process. And this is why we introduce a file system that is implemented in user mode. And by implementing in user mode, can actually bypass and have access requests for including memory mappings and trapping memory and potential delay in that case. So in remote filing system on Windows, basically we can actually bypass the kernel level drivers. How we do so, we can use something called memory write watches, which allows applications to carry memory have been written since last time it was checked, but does not allow us allow memory writes to be trapped. This is why we use exploit or UNC providers MP clients. UNC is just a universal naming convention, as you see, like server / share, which is share folder, and then file, which is it's a way to specify location, resource, and network, and follows the format. And basically, multiple UNC providers part the Windows kernel responsible for UNC paths. When an application tries to access a file using UNC path, the request is intercepted by the MUP. MUP are just a registered client drivers, and that is handled by them, and they basically forward that to a network protocol. So this is why we can actually implement our custom server that can handle reads and write requests to a file mapping and allow us to exploit this vulnerability. And that comes the server message block. It is on Windows that enables applications to use access files of remote servers. It is basically a network protocol used to share files, printers, different resources between nodes on the network. It does follow TCP/IP protocols, which means it has a timeout for that. But basically, this is some pseudocode we wrote just to have an idea of this, how I can custom this. When I have a request type of reading in this case, we can have some delay over there, which is just a thread dot sleep, but every milliseconds we put it over there. It can go up to 60 seconds, which is actually enough, which is not delaying the really definitely, but it's actually enough for our for most vulnerabilities, the 60 seconds in that case. And moving forward with Mina.
Thank you, Brian. For the exploitation to happen, we need these criteria to be met. But as Brian pointed out, SMB doesn't quite meet all the criteria we need for our ideal exploit primitive. So it's time to explore alternative options. One promising choice is the Cloud Files API. This interface allows developers to interact with cloud-based file storage systems, handling tasks like uploading, downloading, and managing files through standard HTTP requests. Initially, the Cloud Files API seemed like a perfect fit for our exploit, since it boasted the ability to provide file contents on demand and support partial hydration, meaning it only retrieves parts of the file as needed. However, when tested with a PowerShell file mapping script, unfortunately, it didn't perform as expected. This is because the cloud filter driver responsible for handling requests for mapping placeholder files was always fully rehydrating the files before completing certain operations. In other words, the API does not provide the capability to delay memory access indefinitely because it forces the file to be fully rehydrated before allowing it to be mapped into memory, regardless of whether the requested file data has been retrieved or not. This limitation prevents the exploitation window from being arbitrarily large, which is a key criterion for our ideal exploit primitive. So we conclude that neither SMB nor Cloud File API individually meets all the criteria for our exploitation to happen. So what if we combine SMB with the Cloud File API? We know that SMB doesn't directly map a file, even locally. Instead, it reads file on demand via the SMB protocol. And on the other hand, the Cloud Filter API allows for streaming parts of a file on demand, as long as the file is not being mapped into the memory. So by integrating these two components, we could leverage the strengths of each to create a robust exploit primitive that meets all our criteria. So by doing so, SMB facilitates the on-demand retrieval of file contents, while the Cloud File Filter API enables the delayed streaming of the file data. So now it meets all the criteria we needed for our ideal exploit. Now, let's explain the process of exploitation through demonstrating the previous example. In this double-fetched scenario, the program checks a condition, the size of the buffer and the type value at one point in time, but then this uses this information later on. So to explain the process, in the first step, we set up a situation where program checks the size of the buffer and the type value. If the size is okay, and the type is valid, the program continues. We then manipulate the timing between when the program checks the size and when it uses the information in the second step. By cleverly arranging the memory layout, just like the pages, we can make sure that when the program accesses the type value, it triggers a page fault or a signal that the required memory is not in RAM and needs to be fetched from storage. This page fault prompts SMB to fetch the required file contents from the storage, allowing us to control the timing of the access. And this third step, the Cloud File API delays streaming of file data. During this delay, while the program is waiting for the type value to be fetched, we can sneakily modify the previously checked size value. Since the program has already checked the size and deemed it okay, it trusts the information without rechecking. Finally, once we've manipulated the size value, when the program finally retrieves the type value, it will just use the manipulated size, potentially leading to memory corruption. So to summarize, through the combination of SMB and the Cloud File API, we were able to exploit a double fetch vulnerability effectively. This concludes our presentation. Thank you for listening and watching to our video. Should you have any questions, please don't hesitate to